All right, I think we're ready.
All
Thank you
right,
so
cool.
much. Without further ado, today we are joined by Sebastian from Google. He's going to give his talk, The Common Android App Vulnerabilities. This is going to be a great talk for anyone that's getting into Android hacking or looking to take it to the next level. So take it away, Sebastian.
Thank you so much. Really appreciate the opportunity here. Um, can you actually, I don't think my webcam is activated, right? All right. I'll, I just have no idea how to do it. Oh, maybe this button did it. Can you see my webcam? Cool. All right, folks. That was a very interesting talk about hardware hacking. So let's see how this one goes. I'm Sebastian. I work for Google, particularly for Android security. And on the Android security team, I work on the anti-malware team. So I've been on that team for the past 8 years. I've uh, analyzed many, many thousands of malware applications.
For a second, we lost your audio there, Sebastian. All right, just 1 second, folks.
Every Android application that we can get for malicious activity. And at one point, we realized that, hey, we can reuse the same code scanner to not just scan for malicious behavior, but we can also just reuse it to scan for application security vulnerabilities or privacy issues, or anything really, any kind of code analysis. And that's how I'm here. And I'll give you a couple of more details in the future. Right now, I am the manager of what's called the Android anti-malware team. That's our reverse engineers. And that's part of the Google Play Protect team. So if you have an Android phone, maybe you're familiar with Google Play Protect, which is just that application scanner thing that makes sure that not too much malware gets onto Google Play. So what is actually the purpose of me talking about security vulnerabilities in Android applications? The purpose is that as part of that idea that we can scan for security vulnerabilities on Android applications, we also acknowledge that there are certain applications that are installed on millions, tens of millions, even billions of different Android phones. And so any kind of catastrophic security vulnerability in top applications can have a very significant impact on the whole Android ecosystem. So far, it hasn't happened. We haven't seen any mass outbreaks of anything because of application security vulnerabilities. And we want to make sure that this is not going to happen in the future either. So we started a couple of programs to make applications, in particular top applications, not just from Google, but also from other companies, safer. I'm going to talk about these a little bit, and then I'll dive into the actual security vulnerabilities. In this talk, I'll mainly talk about 6 different vulnerabilities that I have picked as 6 representative samples of 19 vulnerabilities. And sorry, 19 vulnerabilities that are in 6 different vulnerability categories. And those are the ones that after about 2 years of paying bug bounties for applications on Google Play, those are the vulnerability classes we have identified. Those are the vulnerability types we have identified. And so I figured at one point, I want to show this information to different people. And I created a slide deck. I created a slide deck internally long before I even had an opportunity to present it anywhere. And the first time I presented that slide deck was a couple of months ago at TroidCon Berlin. And you can find on YouTube, if you look for TroidCon Berlin, you can find my talk there, which is fairly similar to this one, but doesn't quite cover the exact same vulnerabilities because I'm mixing it up a little bit. Um, And so I gave it first to a bunch of software engineers who are supposed to build secure applications. And now I'm giving it to a bunch of hackers who ideally want to participate in Android-related bug bounty programs, and maybe to get some ideas out of that. And I'm actually fairly excited that I essentially give the same deck, once from a defensive point of view and once from an offensive point of view. I've never done that before. It's only got an hour, but the full walkthrough takes about 90 minutes to 2 hours. The whole deck with all the security vulnerabilities that we've seen in the past and that we pay out for is actually available on the website of the Google Play Security Rewards Program on hackathon.com/Google Play. So you can check it out later. And that's also obviously the main page where we host the rewards program, where you can find other information and so on. So what did we do a couple of years ago when we decided we want to spend some time and effort to make top Android applications safer? So the first thing we did was we started the ASI program. I think that stands for App Safety Initiative or something like that, or App Security Improvement Program. I always get that wrong. It's a really interesting program because that was the first time we used the scanner that we used in the past to analyze malware to find privacy and security vulnerabilities. And then we automatically took that information and we made it available to developers in the Google Play Developer Console. And for certain problems in the applications, we told developers, hey, it would be nice if you fix that, but if you don't, that's cool too. And for others, we said, you have to fix it or you're going to get suspended from Google Play because the issue is so problematic that you have to do something. And to date, in the last 3 years, essentially, we helped more than 300,000 developers fix more than 1 million applications, which I think is an extremely exciting scale that I believe to this day is essentially the largest scale app security program in the world that I'm aware of. I'm fairly excited about other initiatives that our companies are doing now that are also hosting a lot of applications or a lot of source code. So we'll see if they can beat our numbers. But for now, I still believe that's the biggest AppSec safety program. And then at one point, we ran out of ideas for ASI. We ran out of ideas because there are only so many vulnerabilities, right, that you can think of, or vulnerability classes, at least, that you can scan for. And so even if you had perfect scanners, like how many are there really? There's maybe 30, 40 Android-specific vulnerabilities. And so we decided maybe we just don't know all of these vulnerabilities. And we need to find a way to source new vulnerabilities in the Android ecosystem that we just don't know about. And so we decided, let's launch the Google Play Security Rewards Program, which is a bug bounty program, which started out as a collaboration between developers and Google, meaning you were a top developer, and then first you were invited, and we approached a couple of companies, and we said, hey, why don't you want to join us? You have to do nothing, just confirm with us that a certain hacker found a certain security vulnerability, and we pay out. Companies were excited about that because we end up subsidizing their bug bounty programs, and that's okay for us. The only information we get is information about security vulnerabilities in the Android ecosystem. Then we can use that information to build new ASI scanners and warn more developers at scale that may have similar issues. Over time, we moved a little bit away from the super collaborative approach with developers, and we decided, oh, we don't have to partner with them. We're just going to declare that every application in Google Play that has more than 100 million installs is now in scope for our bug bounty program. And so even if we don't have the collaboration from any of the top developers that have applications with more than 100 million installs, they're still going to be in scope. We're going to triage the bounties, and we're going to triage the tickets, the bugs, whatever you want to call it. And if they are non-responsive, or if they don't have any kind of structured response procedure, and it's going to be difficult for hackers to get the issues fixed, then we're going to work with the developer ourselves, bringing essentially the big stick that Google can bring to the table, and we handle the initial contact and with the developer, and we try to get the issue that you find remediated. And that's really cool. So far, we've paid out nearly $500,000, actually more than $500,000 in the last 2 years. And we've ramped up extremely in the last 90 days. So about nearly 75% of all the payments we ever made were paid out in the last 90 days. There's a couple of reasons for that. The first reason is we went from this collaborative approach with developers to the one that I just described, where every application with more than 100 million installs is in scope. That opened it up a lot from like 50 applications that were in scope to 550 applications that were in scope. So that's a big increase. We also increased the bug bounties. The lowest bug bounty before that was like $1,000 for fairly trivial things, up to $5,000 for a remote code execution in applications. We upped that. The lowest is now $3,000, and remote code execution that's $20,000. And that is very exciting because in these applications that are in scope, many of them have never gotten any kind of security treatment, probably. They've never had security engineers work on them, no audits, no nothing. So they're fairly soft targets. Unfortunately for us, that breaks the bank a little bit, and we're paying out a lot more than we had anticipated. And then occasionally when that happens and we just realize there's a certain vulnerability class in Android applications that just happens a lot, then we also we lower payments, or we declare certain vulnerabilities out of scope, because we have to kind of trade off the budget that we have with the quality and risk and interest of essentially what we care about. So if you read the terms on our website for the rewards program, you'll see that a couple have been moved to $500, a couple have been moved completely out of scope. So be sure to understand what's actually in scope and what's out of scope if you want to contribute. But nevertheless, I think it's a really exciting program that can make you a lot of money really fast, because you pay out a lot for issues that basically nobody else pays out that much. And Android applications, unless you're targeting the really top developers, they're still fairly soft as targets, I would say. So yeah, definitely try to get into that if you want to make some quick cash. If you're a developer and you actually want to understand more, we have a couple of security best practices on the developer.android.com website. There's a couple of other security related topics you want to check out. And then as far as third-party websites go, the two that I recommend here is MITRE.org, which has this common weakness enumeration scheme, which I'm also referring to throughout this presentation. And then there's the OWASP Mobile Security Project on OWASP.org, which is also very interesting to understand what common pitfalls there are in Android security and privacy for applications. So let's start with the actual presentation about the vulnerabilities that I think are worth taking a look at. I think we will quickly find out that a lot of Android applications have these. And if you want to be like some of our top contributors, what they're doing is they built their own application security scanners that specifically target the categories that you're paying out for, and then they just scan every application that is in scope. And so they quickly scale up essentially what they find, and they file tickets against us all the time. That's how we end up with paying out like $350,000 in 90 days. And I think that's a very exciting prospect for all hackers out there. Okay. So the first category I have of the 6 categories is insecure connections. And that's a very easy starter category that most people in this presentation are going to be familiar with that are listening in. Insecure connections essentially come in 3 different flavors. They're not even that different flavors, but I still want to list them out very explicitly here. First one is use of insecure network protocols, and having a category or a class here of or a certain type of a vulnerability in boldface. That means I'm going to talk about it a little bit more on the next couple of slides. I can only take one representative sample from each of these different categories. So for the other ones, please refer back to the full slide deck that is posted on the Google Play Security Rewards Program website. So I picked a very easy one just to get this presentation started, use of insecure network protocols. Then we have data transmission over insecure protocols. The first one is essentially you read from the web in an insecure way, and the second one is you write to the web in an insecure way. The third one is authentication over insecure protocols, which is more or less a special case of the second one. You're trying to log in over HTTP or something like that. Very basic. And so what does it mean to use an insecure network protocol, and especially to read from an insecure network protocol? So what is the problem? The problem is if you load from an insecure network protocol, for example, HTTP, but doesn't have to be. There's Android applications that use FTP. There's Android applications that use Telnet. Anything that is maybe insecure, then an attacker on the same network, on a network they control, they can replace, remove, and inject code. And if you ever gone to DEF CON or something like that, you know that occasionally there's people who intercept traffic there, and then they inject certain images that you don't want to see in your browser or wherever you read the data from. And we want to avoid that when it comes to Android applications, because on Android applications, I'm not very concerned about the idea that someone injects like any kind of prank content, but I'm very concerned that if someone injects phishing password forms, credit card stuff, and so on. So I really want to avoid that. And so I tell top developers that we don't actually like you to make any kind of read connections over HTTP or any other insecure network protocol, because otherwise there's a very high chance that that an attacker on the same network can manipulate that and like throw up something that tricks the user with some kind of social engineering attack into giving up more to the attacker than they should have. And on Android, it's particularly difficult because on Android, there's no such thing really as a trusted UI. And it's funny, I just got an incident chat. Someone wants something, but that's cool. So yeah, on Android, there's no trusted UI, and that makes it very difficult. So if someone has the ability, for example, to inject a legitimate looking login screen into the Gmail application, which hopefully is not possible anymore, of course, but if they were able to do that, then a user can actually not distinguish between a legitimate Gmail login dialog and the one that has been injected, because there's no such thing. There's no URL bar or anything in the Gmail app that tells you this is legitimate. Here's like the gmail.com URL, the green check mark, whatever you have in the browser. So that's very problematic. So we want to avoid that. And yeah, obviously, I give you a couple of auditing tips if you want to find that stuff. And then I'm also, that was more of the developer content. I'm going to give you some tips on how you fix that, right? And it's curious, right? Because one of the most powerful tools for getting started on many kinds of these categories of vulnerabilities that I'm presenting today is actually simple crap, right? You use strings on the app, use crap on the app, and then let's look for HTTP, FTP, SMTP, Telnet, whatever insecure protocol you can think of, and just start auditing there, of course. You can also look at the application's network security configuration, which is a new Android P feature. The security configuration should be able to tell you if an application is even allowed to make HTTP connections, because if the network security configuration says only HTTPS or other secure network protocols, that's an indicator that maybe it's not a good time, not a good way to spend your time to look into that. Understanding common entry points that have anything to do with network on Android, I think is also very important. The most common ones, I think, are the Java classes URL and the WebView class, which is part of the Android AOSP framework. And then, yeah, check the data, the code flows and the data flows that essentially create instances of these classes and set the arguments. Remediation, obviously, since Android P, you can you're fairly safe by default, but if you want to make insecure connections, you have to introduce this network security configuration file that I just mentioned. I just linked the documentation on the previous slide. There's the javax.net.ssl/https URL connection. So you want to use that, not the old HTTP URL connection. It's fairly easy to have like static checks. You can have your own pre-submit checks if you run any kind of source control system or any kind of continuous integration system. You can use an Android lint check if you're using Android Studio to build your applications. So a whole lot of stuff that is there. Nevertheless, a whole lot of applications on Android still use insecure protocols, which is ultimately why we had to downgrade the award for this kind of category to $500 if you find that stuff. Because before that, we paid out $1,000 for anybody who finds that in top applications, and there's just too many top applications that do it. The second big class after insecure network connection is cryptography and authentication. And for cryptography and authentication, I got 3 examples. I think 2 of them are particularly interesting. So let's take a look. The first one is also the one that I'm talking about a little bit more detail, because it actually leads to a lot of questions, not just from hackers, but also from programmers who want to make the application secure. What do you do about third-party secrets that you have, like API keys for Twitter, for Amazon Web Services, for any kind of third-party service that you want to authenticate with from your application? And we pay out $3,000 if essentially you find a security vulnerability related to embedded third-party secrets, as we call them. Here I make a reference to CWE, that's the Common Weakness Enumeration standard by MITRE. So you want to check that out. They have a lot more information about these vulnerabilities and weaknesses than I can talk about in this talk. It's a really cool resource. So that would be CWE 798. One caveat on when I say we pay out $3,000, that doesn't mean we pay out $3,000 on any kind of embedded Twitter API key in a top application. Every time we pay out, we expect there to be some kind of security relevant problem with any of these weaknesses, vulnerabilities, categories that I'm presenting here. If there's no security or privacy related impact, then yeah, maybe you have an embedded third-party secret token. But if there's no problem with that, because you can't actually abuse it in any way, then we don't pay out. And that's a funny story, because obviously hackers would love to get paid out on every report they make, even if it's like not immediately obviously security critical. And then they construct the weirdest attack scenarios and explain, oh, it is absolutely super important that we have to protect this and this and this, even though when we read these very absurd sometimes justifications, we just a little bit amused occasionally, because it doesn't make sense. And sometimes we just tell hackers that just does not meet the bar for security critical. If you want to know what the bar is for security critical, it's also described on our website, so check that out. There's also embedded cryptography secrets, which just means a very common one that I'm not sure if it's happened still, but it used to happen a lot, is that I think WhatsApp stored encrypted chat histories on the SD card when you made a backup. And apparently at one point they used the same key for every single user. So that key was obviously easily leaked because it's embedded in the application. And then a whole lot of spyware that we saw on the malware side just targeted that backup file and tried to decrypt and steal it. And so I think WhatsApp changed. It has been years ago, but still many applications make the same mistake, where they maybe think that kind of cryptography with embedded cryptography secrets is secure, when it's really not, because obviously any kind of hacker can trivially extract cryptography secrets embedded in the application. Yeah, but just by decompiling the code or something like that. The last one is a little bit trickier, leaking OAuth tokens. OAuth is surprisingly easy to misuse, and it's surprisingly difficult. And so if you Google a little bit for OAuth, problems, abuse, mistakes, and so on. You learn a little bit about that. It's maybe less prevalent in Android application. It happens, but definitely far less than the first two categories, I would say. So let's talk a bit about embedded third-party secrets. The canonical example is, yeah, you want to connect to Twitter. I think there's an open source library called Pass Twitter Utils. You initialize it, you paste consumer key, consumer secret, and then obviously every hacker or everybody who wants to do mischief with your API secrets or with your Twitter API can extract these tokens, can impersonate you, and then maybe bad things are happening. And so the question is, what do we do? First, how do we find the problem? To find the problem, it would be nice if you had an understanding of what the most common embedded tokens are, which means you have to understand which are the most common SDKs that are embedded and which of those use any kind of hard-coded credentials to authenticate, right? And common ones that we've seen is obviously there's Twitter, Facebook, Flickr, there is Foursquare, there is Amazon Web Services, there is any kind of other cloud services like Google Cloud and so on. So those are very easy to look for. And once again, strings and key is actually very useful. You look for key, password, login, secret. You can't really just use the strings on that because sometimes, actually you can, but very often it's much better to use the decompiled code because then you also get the easily an understanding of variable names, function names, class names, package names that may also contain like these keywords, and that makes it very nice to triage essentially quickly where's the problematic stuff happening. Remediation is interesting because it's difficult. And there's a lot of developers out there that ask on Stack Overflow or other sources. So what do? I got these Twitter API credentials, but I know that everybody can just easily extract them from my application. How do I protect that? And the quick answer is you can't really unless you spin up a server and essentially you use your own server to proxy these requests to the Twitter API, and you hide your Twitter credentials on the server. You then do a per user authentication to your own server, and then you can at least do some kind of abuse rating on your server to see if anybody abuses what's going on. But if you embed your credentials in the app, then everybody's going to extract them, of course. Now, the good news is a lot of developers give you guidance on how to use their tokens, how to embed them, and so on. And Twitter actually says just embed them in the application and yeah, deal with it. But for the more severe stuff, for the more potentially sensitive stuff, like Amazon Web Services, Amazon actually provides a way for you to, so you don't have to set up the third-party server yourself. They have a whole setup for you that you can use, and then you can use that to proxy the request. And that makes it much easier to keep your stuff secure. So that's nice. From a developer's point of view, you want to understand what are the potential abuses that can happen if my stuff gets extracted. And then you want to formulate a plan to mitigate the negative effects of the abuse. And that really depends. It's hard to give guidance on that because it really depends on what you're trying to protect. Is it a read operation that you're trying to protect? Is it a write operation that you're trying to protect? Is it security critical? Yes or no? Maybe it's not, and that's okay too. So you're gonna, as a developer, you have to think about it a little bit, what's happening. Next category, maybe not as prevalent on Android as it is on other operating systems that are older, especially because Android has a fairly nice sandboxing to protect the files of an application. And so developers really have to make intentionally problematic, if not outright bad decisions to enable private file access. But let's talk about it a little bit. For private file access, we generally pay out $3,000, assuming it's security critical. If someone just has the opportunity to access, for example, the application's default resources. For example, like the resources that are used to show images in a menu, like icons or whatever. If an attacker can read those, we don't care about it because it's not security critical. But if someone can read your own photos or your own private data, maybe worse than photos, yeah, definitely security critical, and we pay out. Private data sharing, in the most abstract sense, is a leak of that data to an attacker. Can happen in many ways. Maybe you accidentally write to SD card what doesn't belong to the SD card. Maybe you write a log file, and in that log file you log personally identifiable information or whatever. But then it gets very quickly very more interesting, because there are a couple of security vulnerabilities or classes of security vulnerabilities that have been known to exist on essentially all operating systems for decades, and they may still happen on Android, and they do happen on Android. We pay out for those fairly often, especially for the one in the middle. Private data override to the path traversal, which essentially means that the attacker can specify a full path that doesn't get sanitized before an internal file is accessed. And so the canonical example is, or it used to be the canonical example when I used to work closer with that stuff many years ago, is that you have a web server. That web server takes a GET request of a file name, and then you do something like dot dot slash dot dot slash dot dot slash, and then user password, whatever. Same is possible on Android, except that instead of like getting the user's local admin credentials or whatever, you get the internal data of the application, which may be critical. Is maybe even more critical if you can override it, because if you can override it, and if you can override code, then you may have the possibility to even get remote code execution or local code execution, for which we pay out $20,000 for remote and $4,000 for local code execution, when you get an application to essentially execute a code that you supply as an attacker. The last one I really like, because it's a very fun class or type of vulnerability: private data override due to zip file traversal. It's a specialized form of the second one, but it's not on anybody's radar. And by default, all the APIs seem to be unsafe. So it's very widespread and problematic, probably not just on Android, but across operating systems. And private data override to zip file traversal is very cool. It essentially starts with an application that accepts or tries to read any kind of zip file that the attacker controls in some way. Can happen in any way. Maybe there's an official way that the application loads a plugin. Maybe you already combined it with another vulnerability that gives you private file access or private file override. And then something really interesting happens. When the application opens the zip file and tries to read it, the content of the zip file is essentially a header that includes information about the directory structure and the file names inside the zip file. And then there's the compressed file entries, right? And the funny thing is that the attacker has full control over what that directory structure looks like. The attacker has full control over what the file names are like. And so they don't just have to be like test.txt. They can be dot dot slash dot dot slash dot dot slash whatever, and then anything that accesses any kind of sensitive data in the usually protected applications. And this is not on any developer's mind, that they, whenever they load a zip file, they need to sanitize each and every file name and each and every file that they're trying to unpack from the zip file. And I think it's a fairly elegant way to attack an application. So how do you audit that? Luckily, there's a standard API that you can search for in whatever application you look for. It's java.util.zip. There's also a couple of third-party zipping libraries. A little bit of open source reconnaissance can help you looking at GitHub, what's popular there. And then understand if your application is in any way loading user-provided zip files. And even if it's not a user-provided zip file, you may have a chance to do a data override if the zip file that is being read by the application is not sufficiently secured. And if you have that, you essentially have an entry point to craft certain kind of attacks against the application where they may leak data to you, or where you can get arbitrary execution inside the application, which is fairly neat. For developers, they need to validate that the canonical path of unzipped files points actually to the directory they want to unzip to, because otherwise it's attacker controlled. You can Google for examples on how to do that. Android zip path traversal. There's some really nice examples that are out there, people have written up. So if you know upfront as a developer that this is a vulnerability, which many don't know, then you'll be helped using these tutorials and blog posts that I found with the same query. The next category is unprotected application parts. Unprotected application parts are very Android specific because they target the way that Android applications are structured and the way that Android applications are actually communicating with each other. Android was built with the vision that applications are supposed to communicate with each other, and that works really nicely, assuming all the applications are playing nice together. But if there is suddenly a malicious application that can then send any kind of messages to harmless applications and try to get them to do stuff they don't really want to do. And yeah, it's fairly it's fairly Android specific. It's fairly interesting actually, because people coming from other operating systems don't necessarily think about that because of the central role that it plays on Android compared to other operating systems. So it's a couple of different things that can be targeted by a malicious application if a vulnerability is hidden there. We pay out usually $3,000 for those. First one, unprotected activity. An activity is essentially a dialog or a UI form or anything like that, or a window if you're coming from that world. Usually you want to have your activities protected if they're part of any kind of critical security flow. Imagine you have two activities, one password and one that gives access to sensitive data after the password is correct. And if you don't protect your second activity, then maybe it's possible for an attacker to bypass that password activity and just hop onto the second one and start that. So that's not great. The second one is unprotected services. Service is something like a background service. The idea is extremely similar to unprotected activities, just for services. Unprotected activities, we get a lot of security reports in the rewards program. Unprotected services, not so much. Typos and custom permissions. This one is really funny because applications can declare custom permissions to protect certain parts of the application, and then only applications that have been granted that permission have access to that. And so, for example, if you as a developer have 3 applications that you want to use, they all have access to sensitive data, say your credit card information that you have with that developer or whatever. That's nice. You can protect that data and only make it available to all these other apps from the same developer. But one thing we've seen is that in at least one report to our rewards program, someone declared a permission and then made a typo in the use. And so you don't get any warning like that from like the compiler, because you don't know who declares the permission and who actually is allowed to receive the permission across the ecosystem. There could be many apps like that. And so essentially the whole permissions check was useless and it didn't work, but the developer didn't notice that until a hacker that worked with our program reported that. And that was it's a very fun one, very, very Android specific, I believe. Intent redirection, we only pay out $500 for that because it happens all the time. And because it happens all the time, I'm going to spend my time on this section on intent redirection. Implicit broadcasts for sending and for receiving are the 2 last types in this category. A broadcast is essentially a message that can be sent from one application to the other. And it's also a way for an application to communicate with other parts of itself. And so if an application wants to communicate with other parts of itself, it should make sure that it only processes broadcasts that are actually coming from itself, and it should make sure that outgoing broadcasts should not be able to be intercepted from a malicious application, because otherwise the malicious application can either steal sensitive data that is part of that message, or they can intercept and manipulate the data, which can also lead to all kinds of problems. Happens all the time too, but not as often as intent redirection. So what is intent redirection? Intent redirection is essentially a very common interface on a really common code pattern in Android applications. The way it works is you get an intent, which is some kind of message. You handle that kind of message, and then you start doing something as part of that incoming message. And usually for intent redirection, and you start an activity. So you get a message that says start an activity, and the activity that you start is actually giving it to you in the message. And so why is that problematic? Because I talked about unprotected activities just 2 slides ago, and that is a very common way for a malicious application to trick a benign application to open a protected activity indirectly. It's essentially a type of confused deputy problem. The good application accepts a message that says, please open this internal, usually protected activity, but the good application doesn't check who gave the command. And so a malicious application can essentially start that activity. And once you realize that an activity doesn't have to be a UI dialog or anything like that, but can also be something very sensitive, like maybe there's an activity that says, oh yeah, every time I'm started, I send photos to a specified URL. Then suddenly this turns into an attack vector where the attacker specifies, oh, start this activity and send all the photos to this attacker specified URL, and then suddenly all your stuff gets stolen, and that's not a good place to be in. And it's very, very common in Android applications, unfortunately. So how do you audit that? I would start with finding all calls of start activity. I would audit that, and then I would verify that intent components are constructed from trusted data. And granted, I acknowledge that this is not very easy because, especially on a fast-moving program with lots of developers, this is essentially a never-ending battle. From a defensive point of view, I would just write my own secure libraries to do that, but I don't think this problem has been solved by any besides the maybe most security-conscious developers on Android. Yeah, you also want to find the calls to intent get extras. Get extras is where whoever is sending the message, be the attacker or not, can essentially give extra information that the application that is attacked is processing. And you want to check that everything is actually arriving from an application, either yourself or a partner application that is benign, that you expect it to come from. It's not enough to check the target class name, because malware can reuse your class names and essentially manipulate your application in that way. It's a very complicated topic. Remediation is always check class name and package name of the target component, not just the class name. And ideally also check the signing key of the app that owns the target component. You only want to send it you only want to send your private messages to the known verified receiver, not to a random application, right? Other is essentially the catch-all category of vulnerabilities. All the ones that are kind of one-off don't really fit into that. And so what we very commonly see here is incorrect URL verification. It's so common that we downgraded it to a $500 reward, but it's actually fairly interesting. That's why I picked it here. Then we have cross-app scripting, which is incredibly common. $3,000 reward. We're probably going to downgrade that. Incorrect sandboxing of scripting language, $20,000 reward, because that usually leads to some kind of code execution. If it's local, it's $4,000. If it's remote, $20,000. The easiest example is you embed a scripting language or interpreter in your application, and then you somehow provide a way for the attacker to give you a script, for example, a Python script that you can happily execute, and then the Python script just steals all your internal data and uploads it to a website. unprotected data on the server. We pay out $3,000. It's not really an application security problem. It's more like a server configuration problem, but we don't distinguish between those. That's the other. So incorrect URL verification. For some reason, it's a very common pattern on Android for developers to try to verify that they're connecting to a certain website that they control, or they're reading data from a certain website that they control. And there's a lot of ways to get this wrong, like a lot of ways to get this wrong. And here's a very common way, or one of the many common ways. It's okay, you have a URI, you call the host of that, and then you look if it ends with yourwebsite.com, right? And obviously any attacker could, for example, just register like, haha, I hacked mywebsite.com, and then you would fit that check. Okay, the next level would be, instead of using ends with, they can just do a complete equals. Doesn't help you. I looked up, I actually asked around at Google, like, how do we securely verify that a URL actually belongs to a website that I control? And it turns out we have code for that I would love to open source, but I haven't had time yet. It will take a while. And it's like 300 to 500 lines of code long. So it's actually really complicated to verify that a certain URL is controlled by you on your application. And that's scary. So auditing, you want to find every instance of URLs being used in an application. You want to narrow it down to those that work on user-controlled input, and then you want to narrow it down even more, ideally to the ones that whose data or whatever or URL name is used to distinguish between code paths, right? Maybe in an if statement, maybe in a loop of some sort. We see all kinds of URL verification mistakes, not just the host name. Can be anything. You can maybe bypass by the typical combo that we see in attacks, not just on Android, but also like on the web, where you inject like fake user password, or you inject a question mark that was not expected, and so on. And the very cool stuff is that someone who is one of our bug bounty top contributors actually wrote up a very nice report that is called Golden Techniques to Bypass Host Validations in Android Apps. And if you read that, it will give you an idea of just how complicated it is to verify that the URL is actually controlled by you and pointing to the server that you expect. And also, of course, from a hacker perspective, how you can bypass a lot of these host validation checks. For developers, the only remediation I have is you have to create a library with the help of your security team that you will always use from now on. At least until I get to the point where maybe one day Google can open source our own library, and then everybody can use that. So I have a bonus if we have more time. We don't really have more time, but I'll fly through it. I've got 10 minutes. So I already talked about incorrect sandboxing of scripting language. The canonical example is really, okay, let's let's include a Python interpreter, and then suddenly I get the Python interpreter to execute malicious scripts that have full access to anything that's going on in my application. In my application's private data has access to all the permissions that have been granted to my application, and so on. But we haven't actually had a vulnerability report that looks as straightforward as this one. We've had a very funny one, like a very funny one that I think is amazing. Imagine there's an application that has some kind of social functionality, and as part of that social functionality, you can create user profiles, you can create your own account images that show up in your avatar when you chat with other people or whatever. And it turns out that in that app that actually has a repository of avatars that people can choose from, and users can upload their own to share with others. And so they used a fairly convoluted image format for that, and that fairly convoluted image format has a scripting language embedded, and that scripting language was kind of sandboxed, but not properly. And so an attacker could actually craft scripts, create an image with these crafted scripts, upload it to the repository, have other people download these crafted images, and then essentially execute code on the victim's Android devices inside the context of the social media application, whatever it was. because every time, or I don't actually know when, but sometimes when maybe the avatar was applied, that the malicious script was executed. And we paid out $20,000 for that. I think we're in the, I'm not sure if we paid it out, but we are about to pay $20,000 for that. So if the hacker who actually reported that to us, it's good news for him or her, I don't know. And that's just a very crafty attack that I think is incredibly sneaky and incredibly cool. I'm going to pass that. I'm running out of time. So I've got, thank you very much. I really appreciate that. Really appreciate you listening to my presentation. I would encourage everybody to start reporting issues to the Google Play Security Rewards program. The targets are very soft. There's a lot of money to be made, especially right now. And Android is fairly easy to understand thanks to the tooling that's available, thanks to being primarily written in Java and or Kotlin these days. And I think that makes for a great hacking environment. So thank you very much, folks.
Thanks, Sebastian. Can you quickly kind of go through how the Google Play rewards program works in terms of researchers reporting a bug, and just kind of go over that real quickly, because we had a couple questions in chat, so I thought it'd be helpful since you have a couple minutes.
I will do that. So first thing you do is you go to Google Play, which is hosted on HackerOne, and you read the rules of engagement and everything. Then you decide, okay, I want to participate, right? And the way it goes is essentially the important part is here. So we don't want to be in the position that we essentially broker 0 days for applications. We don't care about those. We don't even want those, right? And so the very first thing you need to do is you find a bug that's security critical, you report it to the developer. Ideally, they already have a security program, and it doesn't matter where they have it. Self-hosted, HackerOne, Bugcrowd, doesn't matter. You report it to them. And you wait until it's fixed. And after it has been fixed, you report it to us. And we get in contact with the developer. We ask them, hey, this person reported this ticket to us about a bug they fixed. And then the developer confirms, yes, that really happened. And then we just pay you money. And so it's very easy. You report, we confirm, we pay out. That's all there is to it. Do we have other questions?
We've got another question that just came in through chat that's asked, what is the best way to get an APK from a device that is not rooted? Can I trust any third-party APK hosting websites?
So that's interesting, right? Where do I download my APKs? I just, if I don't have access to like my Google tools, I just go to one of the APK mirroring sites. If you're paranoid, check the signing key, see if the signing key makes sense. You can go to VirusTotal, look for the signing key, look for the hash. I'm not that paranoid. I'm actually fairly liberal with what I run on my systems. I also have throwaway devices, obviously, because I'm working in the malware field, the malware analysis field. I don't think you have to be so paranoid if you use one of the very common APK mirroring sites that are out there.
Well, those were the main couple questions that came in through chat, but you're getting a round of applause in the Twitch chat. So thank you very much, Sebastian, for this talk. A lot of people appreciated it.
No problem at all. I'm going to hang out for a little bit on Discord, the Bugcrowd chat. I'm SP there. And in Twitch chat, I'm SPORST, Sporst, that's my name. So if anybody has any questions, please let me know. I'm dropping off the video now. Thank you very much again.